Hi everybody. Due to popular demand, I would like to show something that I have been working on for the last couple of weeks. What you see here is a visual representation of a subset of a dataset that I have just generated. The dataset itself consists of 20,000 heavy metal samples, all of them generated by artificial intelligence. So I have a deep neural network that composes heavy metal sounds or heavy metal music for me. Those pictures, for those who are acquainted with this kind of representation, this is a tile map consisting of so-called MEL spectrogram. A MEL spectrogram, you might ask what's a MEL spectrogram, is a visual representation of a sound, where on one axis, left to right, you have a time, and from bottom to top you have the frequency. Basically, it's a picture that shows you sounds and is very, how can I say, aesthetically pleasing when you look at those things. I zoomed out a little, so this is just a subset. Again, I have 20,000 samples and I think maybe those are 8,000. And then I got a little curious. If I have these samples, I would like to somehow find samples that are similar to each other. And what you would usually do in order to find similarity between samples, and those are not necessarily audio samples only, it works like a charm for images and for texts in those vector databases, that you use an embedding. So I found the clap embedding, looks very promising. It takes as an input a sound, and the output would be an embedding vector. And if you have a vector, you can do math with it. For example, k nearest neighbor, finding out the neighbors of a sample, and also what you can do is a dimensionality reduction. Let's have a look at this one. So I did a dimensionality reduction. How would you do a dimensionality reduction? Either you would do PCA, or you would do TSNE, or you would work with autoencoders. So I decided to work with TSNE. So I took all those 20,000 samples, I embedded them into latent space, and then applied the algorithm on it. And this is where I ended up with. And what you can see here is, we have 3 different colors. And this is already telling something about my dataset. If I'm not mistaken, those here are samples where you have guitar and drums at the same time. And now I have to think. I think this one here, those are samples where you have drums only. And here are samples where you have guitar only. And there are a few that drip in these directions because maybe there's not enough drums in it, or maybe there's not enough guitar, so it ends up in those classes. Okay, and then I thought, well, now I have a 2D representation. What about being able to click into this representation, into this latent space, and then get the sound out of it? And then I thought, well, clicking into a point cloud is quite interesting, but maybe there's another way to do this. And then I remembered when I was an undergraduate student, I remembered there's an algorithm by a guy called Voronoi diagram, Voronoi tessellation, Voronoi plane partitioning, where you would take a set of usually 2D points and you would use them to partition a plane. Here is a good example of a Voronoi diagram. And this Voronoi diagram is based on those points that I've just showed you before, those dimensionality reduced embeddings. And what you can see here is, first and foremost, aesthetically pleasing, and second, for all the points you will see an area with the partition of the space that is closest to that point. So you have quite a lot of spaces for a few of them, but usually they cluster together in some sound. And then I thought, well, this is cool, looks interesting, this should be clickable. So how do I turn this into something interactive? Well, let's turn this into a web application. So I have a web application up and running. This is the same space partitioning. Well, what you can do here is you can zoom in, you can also zoom out, you can scroll in it. That's the first prototype of an interactive application. So let me zoom in a little. There you go, a little zoom. And then I can pick any of these cells, and then I can listen to the sound that is behind that cell. Okay, so we had some drums and we had some guitar. What about this sound? Or that one? Let's go a little bit more to the void. This one. And next to it. What about this one? Ooh, this one is deep. This one? And that one? What about this one? So it looks like we have an area here where we have those deep riffs. What about here? This one is high in energy, and this one? Ooh, very deep and erratic. It's also fast, high in energy, this one. So you see, it's a lot of fun navigating this. So when we see there's this gap from the previous picture, remember there were some canals in it. What about this one? Ah, clearly, this is the drum space, this is drum land. What about this one? And here. And that one. Again, I'm very curious about the fringes. This one. And we have an island here. What is this island? Aha, here's another island. Let's go here. High in energy again. So blast beats, this one. Very, very strong. And there's another continent here. And I think this is guitar only. Let's click this one. And this one. What about this one? What do we have here? Or this? It's a whole landscape to discover. There's not so much going on here. So what about the fringes here? Or there? Or this one? What about this? And now getting closer to the other continent. And back to this one. Why not this one? So what you can clearly gather is that this is quite fascinating. Being able to explore a so-called latent space of audio in order to find samples in it. Maybe you can use it for composition. And this is part of an AI exhibit that I'm working on for KI Salon Heilbronn, where I am artist in residence in this year. So I'm looking forward to turning this into an application, an interactive application where users or visitors to any exhibit can compose music with AI. Thank you very much.